All right, so let's just take a minute and see what our sampling distribution of our difference between two means looks like. All right, number one, whenever you're subtracting, remember you're literally taking population 1 minus population 2, the means, and that is going to be the mean of your sampling distribution. Now, the standard deviation is the addition of the two variances. You're dividing by the sample size since it's a sampling distribution. Okay, so you have your standard deviation squared of your first one divided by your first sample size plus your standard deviation squared of your second sample, all divided by your second sample size. Okay, and then the mean is the subtraction of the population mean, and then the sampling distribution is each individual sample, the difference between each of those samples subtracted, put a whole bunch of dots on here, and that will give you what the sampling distribution looks like. Okay, so just make sure that you're very careful with your symbols. I just wanted to go over them to make sure you know what they mean. Remember, this is your population standard deviation 1, population standard deviation 2, and it's very important that you define what your population 1 and 2 are so that when you write these symbols down along with the numbers, the reader knows what you're talking about. So you have your sample standard deviation 1, your sample standard deviation 2. This is the mean of your population 1 and 2. This is where your null and alternative come from. This is the mean of your sample. Okay, and remember, we always gather sample 1 and sample 2 after we come up with the null and alternative. And here's our population 1 and our population 2. So this is just the population of the sample that we're taking. It's not necessarily the entire population. It is the sample size that you're taking for population 1 and the sample that you're taking from population 2. Okay, so when data comes from two random samples or two groups in a randomized experiment, the statistic x bar 1 minus x bar 2 is our best guess for our value of the population subtraction or the population differences. Well, why is that? Because we don't always necessarily know the population information. Now, when the 10% condition is met, the standard deviation of the sampling distribution of the difference between the means is, okay, we already talked about this, the standard deviation, even though we're talking about the differences, remember we add the variances to get the standard deviation of a difference. Okay, so if I want the standard deviation of the differences, I still have to add the variance. And this is from a previous unit, okay? We already talked about what that means, so if you have questions, let me know. So in the above example, the standard deviation is known. Now, make sure to state this if it's given. And we're going to be going back to our Z and our T statistics. You're going to use a Z statistic if the standard deviation is known. And what do you use if it's not known? That's going to be your T statistic. So if our normal condition is met and our population standard deviation is unknown, we standardize the observed difference to obtain a T statistic that tells us how far the observed difference is from its mean in standard deviation units. All that means is if we don't know this population standard deviation, we use the test statistic T. If you do know it, you're going to use Z. Now, conditions for whenever we're talking about a two-sample test statistic T. Now, most of the time in real life, we're not going to know the population standard deviation, so we are going to take a look at the test statistic T more often than the test statistic Z. Before you start to do any questions with a two-sample test statistic T, you must make sure that you're doing the conditions. And the tricky part here is you're not just doing it for one sample, you're doing it for two samples. So since we're talking about two independent samples and comparing two separate means, both of the samples must be a simple random sample, and the data has to come from two independent samples. So independence here is a little bit tricky because you kind of have two independence conditions now. One is that the two samples that you took are independent, and we're still going to have our population is 10 times the sample size, okay? And make sure whenever you're writing these conditions that you state simple random sample of 20 people, simple random sample of 30. And then when you check the independence condition, make sure you're stating, therefore, independent. So this independence condition is going to be that the population is 10 times the sample size. Now notice you're doing that for population 1 and population 2 because I have two populations here. Also, since I have two independent populations, I have to be able to prove that both samples are approximately normal. The population for both of them can be approximately normal, or, okay, if you have a sample size that's less than 30, remember, greater than 30, you can use the central limit theorem. If it's less than 30, you're going to check the box and whisker plot for skewness or outliers, or you're going to check the normal probability plot, making sure that it's linear, okay? Now, you must show the graphs. Don't just state normal probability plot's linear. You have to show a sketch of the graph. Very important. All right, so let's take a look at the two sample test statistic T. So if the assumptions hold true, so those are our conditions, assumptions and conditions are the same thing, then we can state that the difference, okay, in our sample means is an unbiased estimator of the population mean. So remember, unbiased estimator means that the sample mean is equal to the population mean. Remember, if each population is normally distributed, then the difference in the sample means will also be normally distributed. Now, since we're using a test statistic T, we're not going to know the population standard deviation. So just like we did in the previous units, instead of putting the population standard deviation here, we're going to use our sample standard deviation from sample 1 and our sample standard deviation from sample 2. So once again, remember, this is your formula for your variance of your first sample when we subtract or find the differences to get the new standard error or the new standard deviation of the statistic. That's a big word. We always add the variances. Okay, now this is the standard deviation of the statistic, or remember SE is your standard error, which is the same thing. Now notice, okay, remember we've already talked about this, how it's similar to a one sample standard deviation. The only difference here is you're adding the two variances, then taking the square root in order to get your final answer. Okay, so let's talk about what exactly a test statistic is going to be. So what does our test statistic T look like when we have two samples instead of one? Now, the reason we have T is because we're not going to know the population standard deviation most of the time. It's our basic formula. It's always the statistic that you gather minus your parameter, which usually comes from your null, all over your standard deviation of the statistic. So the statistic that we're talking about here is now going to be the subtraction of your samples, okay, minus the subtraction of the parameters. Now, this value will usually be 0. This one will usually be 0 because we're going to say we always assume that there's no difference in the two population means. And then for the alternative, that's when we say, hey, we think it's greater than, less than, or not equal to. But it's usually going to be 0 because we're going to assume that there's no differences. Okay, so it'll be kind of like subtract your samples minus 0. And then your denominator, your standard deviation, is your variance of the first one plus your variance of the second one. Now, you're going to have to state your degrees of freedom since we have a test statistic T. Okay. When you do that, I would highly suggest getting your degrees of freedom from your graphing calculator. And you're going to need that in order to find your p-value. So to find the p-value, you're going to use the T distribution with degrees of freedom given by technology. Your graphing calculator will give you the degrees of freedom. Or if you're not using the graphing calculator, you're going to use the degrees of freedom is the smaller of n1 minus 1 or n2 minus 1. So you take your sample size minus 1. That's going to be your degrees of freedom, the smaller one of it. So it's kind of the more conservative one. It's going to look less like the normal distribution. Okay. Now make sure you check the calculator on the calculator instructions on how to do this on your graphing calculator, because when you run a t-test on your graphing calculator, Guess what? Gives you your p-value, your degrees of freedom, all that good stuff. Literally the only thing you have to do is plug your numbers in here. You don't actually have to run any of the TCDFs or stuff like that. So I would highly suggest that you learn how to do that. Okay, now the two-sample T statistic has approximately a T distribution with that formula that we talked about. The bottoms are standard error. Remember that the null and alternative is we're assuming that there's no difference between the two. So that number is going to usually be 0. Okay. I would highly suggest using your calculator to determine the degrees of freedom, or this is called the conservative approach when we use the smaller of n1 minus 1 or n2 minus 1. Okay, and that's because it's more conservative, so there's more area in the tails. Okay, so what exactly does our null and alternative hypothesis look like whenever we're talking about two sample means? Your null is we're always going to assume that the means are equal. So mu1 minus mu2 equals 0, and mu1 equals mu2. Those mean exactly the same thing. Now notice I don't have numbers in here. Why don't I have numbers in here? Well, remember, we're assuming we don't know the population mean. So since we don't know the population mean, we're basically saying, hey, we think the population means are equal. The alternative is say, hey, maybe I don't think they're equal. We're asking a question of like, if we don't think they're equal, what do we expect to happen? You can write this a couple of different ways. Mu1 minus mu2 is greater than 0. That's like saying population 1 is greater than population 2. Or we say population 1 minus population 2 is less than 0, or population mean 1 is less than population mean 2. Or, just like our other tests, we say that they're not equal to each other. So when you subtract them, they're not equal. We don't know if one is larger than the other or which one's larger. So those are your 3 different alternatives. Okay, so what you're going to do is same thing. You're going to do your 2-sample t-test. You're going to make sure your conditions are met, state the test you're using, show your work for your test statistic, and then you're going to find your p-value. Now, your p-value, whenever you say population 1 is bigger than population 2, remember that's the colored upper part of your curve. When we say that it's less than, it's the lower part of your curve. And when we say they're not equal, this one is the one that's a little bit trickier, I think. So your 2 probability statements are going to be the probability that X bar is less than, let's use T here, the probability that T is less than 1.5. Negative 1.5 would be down here, and then the other one is the complete opposite, the probability that T is greater than a positive 1.5. So these are going to be the same values, they're just going to be opposite signs of each other.